Will there be an extension?
Extension? For which assignment? I cannot give you an extension of Mark's assignment.
No, Mark has
was
already given an extension. That's right. So now your assignment is before the
we have my assignment this week because it's due on the 12th of December. Do you like the deadline or you want it to be extended? Now the disadvantage of the extension, you will not have the coursework graded back before Christmas for sure. I don't care about that.
We can live with that.
You want me to work hard during Christmas? Okay, so shall we say, now the deadline cannot be postponed after the 16 or 17 because there is a strict, I think that it can be the last day of the term, which I don't know if it is a 16 or 17, I will check. So I cannot give you a very long extension. Okay. It can be only a few days. But if you think that is useful,
yeah, will be.
It is. Okay. So, other questions? That's it? So today I teach the remaining part of the course. And the plan is to, I think it's a bit difficult today for you to see because I'm going to stay there. As I said, there are no lecture notes, so if you want to see what I'm talking about, I suggest you come closer. Unless you have very good eyes. For the remaining part of the course, I will discuss today a little bit about statistical learning theory. So it's a bit more of a theoretical part, which involves probability theory. And so the main goal of the lecture today will be to describe some basic tools through which you can answer questions like, how well will my algorithm do on future data if it has a certain performance of the training data? So these type of questions. And these are called generalization error bound or error bound analysis. And so one important concept that we will see is the concept of complexity, or also called the dimension of a set of candidate models. So we'll go back to regularization or regularize the squares and see how the concept of the dimension plays an important role in answering the question of what is the generalization error of my algorithm. Also discuss a little bit about base bias trade-off. So this is the plan of the lecture today, which I will start in a moment. The other two lectures will be about sparsity methods, so things like the lasso or lasso method, and also multitask learning. So these are a bit more advanced. And so one of the aims is to show you, give you a little taste of some ongoing research in the field. There might be also a half lecture from a colleague of mine who's working on fMRI data, so we will see some application of supervised learning in functional in neuroimaging. Okay, that might be very interesting, but this is not decided yet because she has to go to the NIPS conference, so there might be a conflict. But I think it could be interesting if you can sort it out. I will confirm this week. So this is the plan for the remaining part of the course. And now we start. And you will live here? Can you read over there? Okay. So let me just summarize what you've seen, I think, many other times. So we have probability distribution on the input output. This is our supervised learning problem. It is defined as a distribution, and we don't know it, right? But it exists, and we draw data from it, right? Associated to this probability distribution, we can define what is called expected error, or sometimes called expected risk, right, of a function, right? So this function is could be our classifier or our regressor, depending on whether y is binary or continuous or a real number. And it is defined as the expectation with respect to x and y of the loss function, right? The loss function, which I call here v, could be, for example, the square loss, y minus f of x squared, or it could be the misclassification, right? Loss, the classification loss, right? So this is equal to 1 if y is different from f of x, it is equal to 0 otherwise. So in that case, the expected error is the misclassification error on this task of the function f. So what is the goal of supervised learning is to find a function f which minimize the error. Right? And we know that the best function is called the base classifier. Right? So f star. And the whole problem here is that p is unknown, so we cannot directly compute f star. So our hope is that the learning algorithm will approximate it. And the question is, that we study today, is how well does it approximate? So this is just a slide you've seen many times of the different loss functions that will be used. I think it's just a repetition of what I said. I think you also see logistic regression loss function, right? So, the one here. So you can use different loss functions depending on the problem and depending on what you're interested in. There is also the hinge loss, which is used by several vector machines. If you go back to the lecture 3, I think. So there are many loss functions you can use. So this is a supervised learning problem. We have a data set S that we draw from P, so it's a set of IID pairs drawn from P, and we instead of minimizing the expected error, which cannot be computed because it requires the probability distribution, we try to find a function which minimizes, or in some sense, the empirical error. Right? So the empirical error is the average of the loss function over the determined data. Okay. So this is kind of a natural approach, right? So to look for something which fits well your data. So I think we have seen this in many lectures. So we're discussing squares. There's one way to do it for the square loss. Then we have seen separate vector machines, which is a little bit different. There is also regularizer. So, but there is common ground between these different algorithms that we have seen, right? And now, so the main point is that you need to add some constraints in this minimization problem, right? So because if you minimize the empirical error, right? So what I call the empirical error. If I minimize it, so this is a function of, so you minimize E of S over possible functions, right, which input-output functions. So if your space of functions is very large, there will always be a function f which makes the error 0. So in the case of regression, you interpolate the data, right? So unfortunately, I don't have a board here, but so, right? So if you have, for example, a regression problem, I go here, right? And you have all this data. It looks quite complicated, right? So it looks like that this is like a straight line with noise. But if you use as your space of models, as your space of functions, linear functions like trigonometric polynomials, right, of the size and cosine and different frequencies, and you will be able to go for the data, even if say, they are very irregular, you will be able to go through them, and the error will be zero. But this is a very much irregular function, and so our common sense tells us that you are fitting noise there, right? So if I now draw a new set of data points from the same model, the same distribution, and I try to predict the output with the inputs for this new set of points, the error will not be zero, it will be bounded away from zero. Right? So this function, which here interpolates the point, will not do a good job on the new points. This is exactly what I want to avoid, because I want to learn from the data some laws, some regularity, which also apply to future data draw from the same distribution. So this is the purpose of learning. Right? So you don't just want to memorize your data, as this function does, but you want to learn something about the input-output relationship in general, right? Which applies also to Newton. Similarly, in the case of classification, right? So what is the similar figure? You could have, let's see, something like that. So this is the positive class, and you have the negative class, the crosses, right? And now maybe you have some cross here, some dot here, something like that. And so, if you use a linear classifier, you will find something like that. So with a subtle vector machine, you will find something like that, right? But again, if you use a nonlinear classifier, you use a Gaussian kernel, for example, polynomial kernel of high degree, you will separate exactly the data. So you will find something like that. So this point keeps it away, something like that. Right? But the decision boundary is very irregular, right? Again, and maybe you fit the noise. So there is some labeling noise in the points. So you could imagine that some of these points, like say this one, right, and this one, they are a result of labeling noise. So there is a human observer which, I don't know, looks at the database of images, and he has to tell you if the image is a person or not, and sometimes he makes a mistake, and that is a source of. So, if you have a large space of function, you can always fit exactly the data, but you need to be careful because you might overfit. On the other hand, as we have seen in the course, you cannot just use linear models, because linear models are very simple, and if you have enough data points, you have reason for looking for nonlinear relationships. So you have a reason to consider a larger space of functions. Right? So the question is that we try to discuss today is how big can be the space of function so that we can safely work in that space. So this is the kind of question, right? So if it is too big, we will always fit exactly the data, but it will be overfit. But so how big can it be? And clearly here, the question is a tricky question. But for sure, one important point is how many data points I have. So the straight answer is that count how many data points you have, count how many parameters you need to specify to identify a function, and maybe the ratio between these two numbers or something like that is what will enter right into the analysis. And the answer is pretty much like that. It's a bit more sophisticated, but right. So if you have 100 parameters, and you have less than 100 points, you are in trouble. Right? It is not as simple as that, but it's that direction. So this is just a quick summary of regularization. So one way is to minimize the error, subject to a constraint on the parameter space, on the function space. And the other way is to do to directly minimize the error plus a regularizer. So these are the algorithms that we have seen are of this type rather than the first type. Right? So you solve an unconstrained problem in which rather than say that, for example, the weight vector needs to be less or equal than something, so this is a way to constrain the space of functions. Right? You directly have it in the minimization problem. Right? So, but the problems are related because you can show that if you minimize the empirical error, which is this is what before I call E of S, right? Empirical error. If you minimize the empirical error, it's subject to some constraint on the function, so in this case on the weight vectors. This is equivalent to minimize empirical error plus a parameter times the norm of the function, of the square norm. So there is a one correspondence between A, which controls how big your parameters can be, and lambda. So this is one figure which gives you some idea. So there will be a parameter which controls the complexity of the space of functions, right? So for example, this parameter A in the previous slide, right? Or the parameter lambda in an implicit way, right? And the larger the parameter, which we call the model complexity, right? So the larger the set of functions, the smaller the training error. Right? So this is the training error, this blue line. However, right, if the model complexity is very large, there will be a gap between the training error and what here is called the test error, but is the same as the expected error. Okay. So this is the error of the function on the training data, and this is on a new set of data generated by the same model, by the same P of X, Y. And another way to explain this discrepancy, so this overfitting, right, is based more on classical statistics, is the idea of bias and variance. I will also briefly mention at the end of the lecture how this issue is addressed in classical statistics. So the idea is that if the model complexity is very high, right, in principle, in the space, there is a function which can go close to the base function, so base classifier, I think it's called the base regressor, so the optimal function in the space, the function which minimizes the expected error. So there is a very small bias, right? So your space is so large that you can find exactly or with a good approximation the underlying function. However, since the space is so large, depending on which sample which training set you obtain, the solution is very fuzzy. It changes a lot, so there's a big variance. Right? For this reason, there is this gap. Right? When the model complexity is low, there is a high bias because the space of functions is small, so the optimal function there, which minimizes the expected error, will be quite different from the optimal function which minimizes the expected error with no constraints. Right? However, the variance will be small. So again, there's a trade-off between bias and variance, which also plays a role into the classical statistical analysis of our learning algorithm. So we'll go back to this. Right. Just to summarize, also, I think this we have seen before. So another important issue is how do I choose, this is the issue of model selection, right? So how do I choose my model? So, this means that you use a learning algorithm which depends always on some hyperparameters or additional parameters. So for example, it could be the lambda of the ridge regression, or the parameter A when you use the constraint on the weights, or any other parameters which appear in your learning algorithm, right? So k nearest neighbor was the number k. What we will see today is that we have a collection of hypothesis spaces. Maybe they are nested, they grow. And so which one do I choose? Right? So this is the aim of model selection. So the classical way to solve this question is to do cross-validation. One of the widely used methods is to do cross-validation. Right? So you, this is just a summary of what we have seen before. So if you have a large data set, what you do, you split it into 3 parts. So you have, most of the data you use them for training, and another part of the data you use for validation, right? So validation means choosing the parameter lambda or choosing the parameter k. And the remaining part of the data you use to assess the choice of your model, right? So you see how well it works. So the last part of the data is used to have an estimate of the test of the expected error of your model. But there is a problem here. The problem is that if the initial data is very small, here you sacrifice part of the data for validation and testing, whereas you would like to use all of them to train your model because they are very small. So what we discussed today is generalization error bound are in principle a way to use all your data for training and still be able to say something about the performance of the model afterwards, right? The performance of the solution afterwards. So what we discuss is it's also called learning theory, machine learning. So it's a direct way to relate the training error to the expected error, also called the generalization error. So generalization error is the same as expected error. So traditionally in machine learning, this term was used, but it was the same as expected error. Just a repetition of what I said. The data are IID from some distribution, right? So now what is important, this slide is important to fix the notation. So we have the data, right? And that's our main actor in this supervised learning is a learning algorithm, right? Which here I call A, right? Script A. So, what is a learning algorithm? Well, let's think of the deterministic algorithm. So, it's a function, right? A, which, given the training data, outputs a solution, right? So, a function, right? And here I put the script F to remind you that the solution is found within a set of functions. Okay, so this is a very abstract notation for something which in practice is much simpler. Right? So there is a set of functions, for example, could be linear functions with some bound on the weight vectors, right? So like image regression. There is a training set, then there is an algorithm, a machine, which given the data and given the function space, search within the function space the function which has the smallest training error. So this is a learning algorithm. It doesn't need to be based on the minimization of the training error. It can be any other function that, given the data, finds you a function through which you can predict the output of an input. But let's say the default algorithm is empirical error minimization. So this is very important. Is it clear to everybody, this notion of learning algorithm? Are there any questions? Okay. So, what do we want to do? So the first important thing to realize is that the solution of the learning algorithm is a random variable, right? Why it is a random variable? Because depending on, so the randomness is due to the selection of the training points. So since the training points can be seen as a random variable because they are IID random variables sampled from P of x comma y. As a consequence, the solution of the learning algorithm, which you can think as the weight vector of regularized least squares, right? So will be a random variable. So the question of learning, right, so the statistical question, is what can we say about the expected error of the solution, right? Or any other statistical property of the solution. So the key quantity we're interested in is the expected error, which I denote as epsilon of S, right? Because it depends on the training data. So S is the training data. A is the algorithm. F is the function space. So this is expected error. So the expectation over x comma y, expectation x comma y from my model of the loss, right? Of my solution. This is a function, like would be w hat, right? At x comma y. So all this complicated thing, it's actually, let's give an example to make clear that it's simpler than what it looks. So I have my data S, right? On my data S, I do bridge regression, let's say, and I find the weight vector W, which I call WS, right? And then I want just to do the error of this vector. Right? So the error will be the expectation over x and y, so it will be the integral over p of x comma y, right? And then it will be a loss function. Let's say the loss function is just a square loss, so it will be ws transpose x minus y squared, the epsilon. So this is epsilon s of bridge regression, let's say, and that's it. Oh well, there is also some parameter here, the regularization parameters. Does it make sense? That's an example of what the algorithm would be.
Could you just move up?
Yes. This is not very. The big room with more screens. So we want to say something about this quantity. So this is still a random variable. That's the other important thing to mind, because here I've taken the expectation of the input-output, but S, I haven't taken the expectation of the S. So this quantity, which I call the generalization error of my learning algorithm, right, is still a random variable because S is a random variable. Okay, so it can take many values. So one main point of this lecture is to show you how to control the variance, the fluctuation of this variable. So another example is you have k nearest neighbor, right? As your algorithm, which is not empirical error minimization, is another algorithm. It's very powerful, right? Because you can output vary, reach, say, decision boundary classification. That k acts as a complexity control parameter, some regularization parameter, right? Because the larger k, the more the smoothing you do. Again, so in this case, you want to understand how this random variable behaves with k. Have you seen the Decision trees? I think Mark spoke about them. That's another important algorithm, which is like more a greedy algorithm. It's a beautiful algorithm, it's very useful in application. And there again, if the tree is very deep, you have a more complex model. And again, you would like to say something about how the generalization error of your solution depends on the depth of the tree. So we will not answer all these questions, so these are they require more time. We'll just discuss part of the problem, so the core of the problem today. So there are books which just focus on these issues in detail, go through all the possible outputs. Yeah. So I think this is just repetition of what I was saying. We will start with the case in which we'll start with the case of binary classification, and then I will discuss also regression in general. So just to remind, so V is equal to 1 if the two disagree. So we have the true output and the predicted output. Right? So if they disagree, the loss function measure is 1, otherwise it's 0. So in this case, the expected error is the probability of making an error on a randomly chosen input-output pair. Right? So what I start to discuss is a simple example, which is very instructive, on what's going on, right? So a bit more in detail when you increase the complexity of your algorithm. And the algorithm that we describe is what is called, it's very simple, at least for classification, it's called the parser window classifier. I think, have you discussed that in the course? Well, the simple algorithm, which is natural, intuitive, right? And here we see a simulation that some student in the past did. So these lecture notes were prepared mainly by John Taylor and a few years ago, and I've done some addition to them. And so this is a simulation that they did, taking this breast cancer data set. So it's a binary classification problem in which you want to predict the chance that the subject has breast cancer. So you have two classes, and how do you do that? Well, a simple classifier is to compute, so you do a linear classifier, right? And the weight vector for classification is the difference between two vectors where W plus is just average of the positive class, and W minus is the average of the minus class. Okay, that's what it is. This is actually not exactly this is the parser window classifier in a limit. Because typically, a parser window, this wall window, you also weight. You do a weighting of your samples. So you have all your samples here and there. You have a new input that you want to classify. Right? Then you do the average by weighting with a curve which measures the distance between the point you want to classify and all the other examples. Right? So you do a weighted average of the positive, a weighted average of the negative, and then you decide it's positive or negative. The same algorithm works for regression. Okay. So, right. So let's see what happens to the expected error, the generalization error of the parser window classifier as a function of m. Okay. So what we can do, so what this example does, is we repeatedly compute the generalization error by sampling many times the set S. Right? So the set S has m points. We can choose these m points many times, and we see what is the distribution of this random variable. So what is the average, what is the variance, what is the shape of the distribution, right? And this will illustrate the risk of overfitting, right? So again, we have our training set. We do this parser window classifier. We compute the test error, well, the expected error. In practice, we will compute this by taking an average over a big set of points. Right? And then we look at the generalization error, and we repeat this again. And this way, we have an histogram of the values of the expected error. Okay. And what we will see in a moment is a plot of this histogram, right? And we repeat this for many values of m. Okay. So there is a little twist here, right? And so and m decreases. It goes from 342 to 7. Okay? So 342 is the size of the full data set. So yeah. So in this simulation, I assume that my world, right? So my probability distribution for which I draw data is supported on these 342 points. Right? So when n is equal to 342, I always get the same answer. So these are zero variances, like a delta peak. But as m decreases, depending on which, so if I have 273 points, I can choose them in many ways, right, for my all possible set of points. So these will have some fluctuation. As m becomes smaller and smaller, the fluctuation will increase. So the example is, in a way, is very intuitive, I think, as you will see. Right, so this is just to remind you our classifier, what it is. This is an example that you can reproduce yourself if you want. You take your data set S and right. So this is the average of So you can also see that if you take the expectation, so you can take the expectation, right, the expected classifier that you obtain by this procedure. So every time you have a set S, right, you have a classifier, you can look at the, on average, what is the classifier that you obtain. And since the classifier is the difference by the positive and negative weight vectors, then you see that on average, right, the partial window classifier is the difference between the conditional mean of the positive class minus, so the mean of the positive class minus the mean of the negative class. So that's what the classifier tries to do, right? Right? So we use a nonlinear loss function to measure the expected error, the generalization error. So, so the expectation of the generalization error is not exactly equal to the generalization error of this, but approximately we say that it's equal to that. So, right. And here, this is when you go back to the computer, but so again, if you use the full data set, this is your generalization error, there is no fluctuation. Then you start to decrease it, right? And then we decrease the gain, right? So that doesn't change much, right? Actually, if you see here, it starts to grow something here, and then let's see, decrease the gain, right? And then more, right? Like the distribution of the generalization error starts to be more spread out, right? So this is the histogram, well, the fit distribution. The histogram over many draws with 68 points, right? From the full data set. Right? You compute the Poisson-Rigo classifier from the 68 point, and you compute the test error, right, on the others, and you see how much this test error changes over the draw, 68 points. Okay? And the smaller the number of points, the larger the variance with distribution. Right? So if you keep doing that, it becomes really spread out. And so we get this. Well, as you can see here, right? This is the this thing is the expected error, right? So there are some classifiers which make more than 50% error. They completely get it wrong, right? Some get 60%. So if you just have 7 points, it's very difficult with 7 points to say anything. But the average is still pretty good, 0.28. So on average it works not that bad, so it classifies correctly most of the points. But there is a big thing, right? There are some classifiers which are worse than random chance. So what is the moral of the story? Right? The moral of the story is, so I want to introduce the next topic, which we will start after break, is that it is not good to look at the average of this distribution. Right? And so traditionally, in statistics, when we see the end of the lecture, so you look at the average of the error of your classifier over the training data, right? And you look at that as a measure of performance. So this will be the average of the distributions of these histograms. This is good, but doesn't give you a full picture of what's going on, right? Because there could be a big variance, right? So there's a big tail there, and if you have only 7 points, maybe the average is 0.20, 8, but you also want to make sure that there is a small probability that the error of the classifier will be bigger than 0.35. So the average is 0.28, but you want to have a guarantee, right, that what you learn will not be worse than something. And so this is what we will see after the break. So how to make such a statement that the performance, the generalization error of my model is with high probability less or equal than some value. This is just the definition of the basis. And of course, as the sample size increases, right, so the performance of certain algorithm becomes closer and closer to there's an error, right? So it becomes closer and closer to the expected error of this big epsilon of the base classifier, right? But this is in the limit. Whereas here we want to deal with this problem. We have a finite training set which might be very small. Can we still say something about the performance of the algorithm? Right. So I think we can stop here. So traditional statistics, as we have discussed right now, must concentrate on the mean of the distribution of the generalization error. But this quantity can be misleading because it can have a big tail. So what we will discuss after the break is a way to control the tail distribution. Okay. So stop for 5-10 minutes. Unless you want to continue and you want to break. Is it a preference? Break.